Alright, so now we're going to look at hyperbolas. Hyperbolas are a kind of like a parabola, kind of like two parabolas, but the general equation looks like an ellipse, or the standard form looks like an ellipse. It's a big mess. But anyway, a hyperbola is where we cut two cones vertically, and the shape that we get is a hyperbola. So let's look at some real-life examples of hyperbolas. Well, first, let's look at the mathematical definition, which is the set of all points in the plane, the difference of whose distances from two fixed points called the foci remains constant. So for an ellipse, the definition was almost exactly the same, except for instead of difference, it was the sum. But for a hyperbola, it's the difference. Again, there are two foci, plural for focus, or, yes, sorry. And so this is our definition of a hyperbola. Where do we see them? We see that in architecture. We also see it in nuclear power plants. The stacks of a nuclear power plant are hyperbolic in shape. When a plane breaks the sound barrier, it actually creates a cone around it that is a shock wave. But when that shock wave hits the ground, it is then being sliced by the ground, so the wave moves across the ground in a hyperbolic pattern. A few other examples that you see more often would be if you just look at your face in the mirror. The way your nose separates your eyes is forming a hyperbola. If you look at a basketball from the top and you look at the lines on the basketball, also creates a hyperbola. Just a few other examples. So anyway, standard form of a hyperbola. X minus a squared over a squared minus y minus k squared over b squared equals 1, or y minus k squared over a squared minus x minus a squared over b squared equals 1. Center is the point hk, so that has not changed. The circle, the ellipse, and the hyperbola all have a center at hk. A is the distance from the center to the major vertices, same as before. B is the distance from the center to the minor vertices. They're technically not called minor vertices, but just to make things easier, we're going to use the word minor vertices for this. And C is the distance from the center to the foci. Now, a couple of differences from the hyperbola to the ellipse. So with the ellipse, A was the largest number, comparing A and B. With the hyperbola, A does not have to be the large number. A is going to be the number with the positive squared term. So notice the key difference from an ellipse to a hyperbola is that we have a minus in the standard equation. So if y squared is positive, not this part, but the y, because here if this minus is here, then the x squared is actually negative. If y squared is positive, then we are going to have a vertical transverse axis. The transverse axis is the same thing as the major axis. If x squared is positive, again, I'm referring to the coefficient on the x squared term, not this term here, not the h, but the x squared. If x squared is positive and y squared is negative, then we have a horizontal transverse axis. So what does that look like? So horizontal would be our hyperbola is in this direction. We would have some center here, HK. This would be our A. And then we would have some foci here and here. And we would also have a major vertex there. And then this distance here would be our C. And B would be some other distance of a point that we can't, that is not actually on the graph, like here and here. So our relationship between A, B, and C now is the actual Pythagorean Theorem. So this is different than with the ellipse, where it was a squared minus b squared. For the hyperbola, it's a squared plus b squared. Our vertical transverse axis. So now that means the shape of the hyperbola is going to look kind of like this. Again, we would have some center, HK, and then I would have major vertices, boom, boom. This distance here would be my A. We have some other other thing here. Let's call this here and here. So this would be my B. Again, we'll talk more about that when we get to actually doing stuff with these. And then I would have, let's call this here, here, and this would be my C. So the point is, A does not have to be the larger number here. A is just the one that goes with the positive coefficient for the squared term. Alright, let's do an example that'll make things easier. So, x minus 2 squared over 9 minus y plus 1 squared over 64 equals 1. Center is the point 2, negative 1. Notice that the x squared is first, y squared is second, y squared is negative, therefore this is going to be a horizontal transverse major axis. I see that my a squared is 9, so a is 3. B squared is 64, so B is 8. So this is an example where the B value is larger than the A value. That's okay. Alright, so what do we do to graph this? We actually start out the exact same way as we did with the ellipse. So first plot the center to negative 1. Now, A was the number underneath the x's, so that's how far I go left and right. So I'm going to go left and right 3 from the center. 1, 2, 3. 1, 2, 3. I'm going to go up and down 8 from the center. 8. 8. Now the difference is, instead of connecting this and drawing a lovely ellipse, we're actually going to draw a box. So to make it so we recognize the box is not actually part of the graph, I'm going to use this blue, and then I won't use the blue again. So here's my box. Ideally I would do it dashed, but the computer doesn't react well to dashed lines. So anyway, we draw that box. What does that help us with? Well, now we're actually going to use the box to draw our asymptotes. Asymptotes, you say, what? How do we find those? We'll talk about that in a second. What are the asymptotes? The asymptotes are going to be the diagonals of the box. So diagonal, 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 diagonal. Perfect. Couldn't draw it any better myself. Alright, and then we actually draw the hyperbola. So from the vertice here, it's going to curve along the asymptotes. From this vertice, curve along the asymptotes. So what I want to point out is the red curve is the only thing that's actually the hyperbola there. Everything else was just used to come up with that curve. So, major vertices, we can write those. I see I have the point 5, negative 1. And I have the point negative 1, negative 1. Notice that we don't really write minor vertices for this. The foci. Oh, forgot about those. Alright, so I know 64 plus 9 equals 73. So C equals the square root of 73. Square root of 73 is like 8 point something. So from the center, I'm going to go to the right 8 point something, so I'll have a foci there, and I'm going to go to the left 8 point something, so I will have a foci here. So the foci then are going to be the point negative 2 plus or minus the square root, I'm sorry, positive 2. 2 plus or minus the square root of 73, comma, negative 1. So I added and subtracted the C value, 73, to the X value of the center, and then the Y value did not change. Asymptotes. How do we find those? Well, we drew the equation of this line. So we know that from the center, I went up 8 over 3. So I know I have a slope of 8/3. From the center here, I went down 8 over 3. So that has a slope of negative 8/3. And we know that they both went through the point 2, negative 1. So I have a point and I have a slope. I can write the asymptotes. So we're going to write y plus 1 equals plus or minus 8/3 times x minus 2. Those are our asymptotes. Alright, I want you to try the next one here. Notice this is going to be a vertical transverse axis. You're going to do everything the same, but the shape of the graph is going to go up and down instead of left and right. Everything else stays the same though. Pause the video, try to do that, unpause when you're ready to check. Alright, so our graph here should look like this. The hyperbola is opening up and down. We've got our foci here and here. So my major vertices are 5, 2, 5, negative 8. Asymptote is y plus 3 equals plus or minus 1, times the quantity x minus 5. And my foci is 5, foci are 5, comma, negative 3 plus or minus 5 root 2. How do I come up with that? I look at my equation. The center is 5, negative 3. A squared and b squared are both 25. So a is 5 and b is 5. 25 plus 25 is 50. So c is 5 root 2, which is the square root of 50. But since the a was with the y term, that's how I know it's a vertical transverse axis. So I plot the center, 5, negative 3. And then I went up 5, right 5, down 5, left 5. I drew in a box. I drew in the asymptotes. And then I just drew a lovely curve for my hyperbola. I plotted the foci approximately. The square root of 50 is a little bit more than 7. So since this was a vertical transverse axis, that means I plot them up and down from the center. And so then again, once I do the graph, it's actually easier to see these points. That's how I got 5, 2, 5, negative 8. The asymptotes go through the center, so that's the point 5, negative 3, and they both have a slope of 1 or negative 1, so plus or minus 1, and then I wrote the foci. Alright, so that's if we're given the equation in standard form. What if we're given the general second degree equation? What do? Panic? Maybe, maybe not. We have our general second degree. Again, we're going to look at the a and the b. What do we care about? A and B have to have opposite signs. They can have the same value, they can have different values. They need to have opposite signs. That's it. If they have opposite signs, and this is iconic, it will be a hyperbola. So, what do we do here? Same thing to start. I see that there's my A, there's my B. This is a hyperbola because those are opposite sides. Now I want to go ahead and put this in standard form. So I group the x's and group the y's. The difference with the hyperbola, take the positive one and put that first. So I'm going to write this as 16y squared plus 64y minus x squared minus 2x equals 65. Now I have to get my leading coefficients of the squared terms to be 1 before I complete the square. So with the y's, I'm going to factor out a 16, and I'll be left with y squared plus 4y, leave a little space. With the x's, I'm going to factor out the negative 1, because I want the negative outside the parentheses. Then I'll have x squared plus 2x, leave a little space, equals 65. Go ahead and complete the square. Half of 4 is 2. 2 squared is 4. But if I add 4 times 16, I actually have to add 64 to this side. Half of 2 is 1. 1 squared is 1. But if I added 1 and it was multiplied by a negative 1, I actually have to subtract 1 from this side. Now, before we go on, I'm just going to pause here and we'll start video 2 with the completing of the square.